Welcome to the content material for Class 20 of Engineering Statics. You should be watching this video before your 20th class. In this lesson, we will learn how to draw shear and moment diagrams for two-dimensional beams. In our last class, we learned about the three internal forces: the normal force, shear force, and bending moment. We usually assign the letters N, V, and M to describe these forces. Beams are important structural members that are designed to support loads applied perpendicular to the cross-section. For example, this bridge has several beams that will support the bridge deck on top. Knowing the shear and the moment at every point along the beam is important for the design. The normal force is not usually considered, since there is often no normal force, and because it's not usually important to design. Therefore, we can draw a diagram that shows the shear and moment at every point along the beam. Knowing where the highest shear or bending moment occurs and how high that value is can help us design the beam. In this lesson, we will learn how to draw shear and moment diagrams for beams that have only concentrated forces applied to them, no distributed loads. We will address distributed loads in the next lesson. So here's the procedure for drawing shear and moment diagrams. First, determine the support reaction forces. In this example, the supports are both 2.5 kilonewtons. Second, draw two x-axes representing the length of the beam. One for shear, labeled with a V, one for moment, labeled with an M. Third, start the shear diagram. Starting at the end of the x-axis with the value of the external force at that point. The external force on the left is upward, so a positive 2.5 kilonewtons is where we will start. Then continue the shear diagram with a straight line until the next external force, which occurs at x equals 2 meters. Add or subtract depending on if the force is positive or negative on the y-axis. The next external force is at point B, where a downward 5 kilonewton force is applied. Downward is negative, so our shear diagram goes from 2.5 kilonewtons down to negative 2.5 kilonewtons. And repeat for the next section, continuing in a straight line until done. So in this example, the line continues over to the end of the beam where the upward 2.5 kilonewton force brings the shear back to zero. The fourth step is to go to the moment diagram and start at the beginning of the x-axis with the value of the moment at that point. The moment in this example is 0 at the end, so we start at 0. Then, determine the area under the rectangle for the shear diagram. The area of this rectangle is 2.5 kilonewtons times 2 meters, or 5 kilonewton meters. Then add or subtract that amount to the moment diagram, depending on if the shear is positive or negative. The area is positive 5 kilonewton meters, so our moment diagram goes up from 0 to 5. And then repeat for the next section and continue until the end. So in this example, the second segment has an area of negative 5 kilonewton meters, so we move from positive 5 back down to 0. So our moment diagram looks like a triangle. I'll show you how to work through some examples. So this time, instead of finding the shear and moment at a single point, we want to draw a diagram that tells us the shear and moment at every point. But the procedures will be very similar. First, we have to solve for the reactions. So here we have a fixed joint at A. So in our free body diagram, we can start with the external force. And here we have a moment, potential X force, and a potential Y force. And so we have to solve for them. Solving for the forces in the X direction, AX equals 0. Summing for the forces in the Y direction, we find that AY is equal to 6 kilonewtons, and taking the moment about point A, we can solve for the moment about point A and find that it's 18 kilonewton meters. Now that we have reactions, let's start drawing our shear and moment diagrams. So first, I'll start with the shear. We always start with the shear diagram. So here's a positive shear, here's a negative shear, and this is moving along in the X direction. We know that we'll go a distance of 3 meters. That's the length of the beam. And what we do is we look at X equals 0. What is the shear? Well, the reaction at AY we know is positive, it's upwards, 6 kilonewtons. So I'm going to start here with 6 kilonewtons. And the next thing I do is I will continue in a straight line until the next external force, which doesn't happen until we get to the end of the beam. There are no forces or moments applied until we get to the end. And here we see a downward 6 kilonewtons. So I'm going to go down from 6. 6 minus 6 is 0. And so I end here at 0 kilonewtons. And so this is my shear diagram for this beam. Now I can take that information and create a moment diagram. So I use the same x-axis that has a distance of 3 meters, a length of 3 meters. And same thing, I'm going to start with what I know. I know that over here we solved that the moment about at the point A is equal to 18. In fact, it's a negative moment. Now, why is it negative? Well, look at the direction that the beam is bending. So this moment tends to bend the beam downward. And if it's a downward, we call that a negative bending moment. So we're going to start at negative 18 kilonewton meters as the bending moment. And I'm going to continue from here until I get to the next external force that's applied. And like we saw, the only external force that's applied doesn't occur until x equals 3 meters. So I'm going to find the area of this rectangle up here. So this area is 6 kilonewtons, that's the height, times the length or the width, which is 3 meters. So the area of that is positive 18 kilonewton meters. So I'm going to start at negative 18 kilonewton meters, and I'm going to go up 18 kilonewton meters, which of course brings me to 0. So I'm going to draw a straight line from 18 to 0, and that will be the shape of the bending moment for this beam. Okay, in this example, we follow the same procedure. Start with the reactions. So we have a beam. So here we have AY, AX, and the force B. And don't forget to include that we have a moment applied, and I'll call that the moment C, which is equal to 30 kilonewton meters. So let's start with solving for the x. We find that AX equals 0. Some of the moments about the point A show us B. So here's our external moment that's applied. We can solve for B. Find that B is 5 kilonewtons. And finally, we can solve for the sum of the forces in the y direction. Find that A is negative 5 kilonewtons. So we assume that AY points in the wrong direction. In fact, we see that AY is downward. Okay, so we need to remember that going forward. So let's start by doing our diagram. Let's start with the shear diagram. Okay, we have positive shear, we have negative shear, we have our x-axes, and we're going to start with a negative shear. We saw that AY is downward. So there's a negative shear, and the value is negative 5 kilonewtons. And we're going to continue in a straight line until we get to our next external force. Well, there's a moment applied here at the middle, but there is no upward or downward force, right? So there is none of this. So we can continue on until we get to the point B. At the point B, there is a positive upward 5 kilonewton force. That brings us back to 0. So again, we have a single rectangle that makes up our shear diagram. Now we can move on to drawing our moment diagram. And so the length of this is the length of the beam, which is 6 meters. And this is halfway down the middle. We're going to need that information later. So our moment diagram, we have positive and negative. So if we start at the point A, we see that there is no moment. There's no moment at the point A. It's a pin. So that's our starting point. And the first thing we're going to do is we're going to say, what is the area of this rectangle? This rectangle is 3 meters wide and has a negative 5 kilonewton height. So that means we need to go down 15 kilonewton meters. So we start at 0 and we draw a straight line down to negative 15 kilonewton meters. Next, we have a moment applied, and this moment curls this way. So over here, does that curl it upwards or downwards? Well, looking on this half of the beam, on the right half of the beam, it's going to curve it upwards. So that's a positive moment. So what that means is we have to go up 30. So from negative 15 to plus 30, so negative 13 plus 30 equals positive 15. So we're going to go up here to positive 15. And now we're going to figure out the area of this rectangle, which is the same. It's minus 15. So we start at positive 15 and we're going to go down 15 and reach to 0. And so here we see the moment diagram. Looks like two different triangles here. So again, the reason for this is that there is a moment applied here. And it's a positive bending moment. Okay, so that's it for this. These examples. Be ready for the quiz, and in the next class, we'll see that there's a method to this madness, and there's a mathematical relationship between the loading, the shear, and the moment.